Good afternoon, colleagues and friends. So I'll be taking you through the lecture 57 uh, with the title Decision Support System and Modeling in CBR and Emergencies. If you remember in the first part of our course, I had discussed a few issues or explained the basis of taking emergency response actions, the fundamental technical basis, and the various frameworks that are put in place for taking emergency, for ensuring preparedness and response for nuclear and related emergencies. And I have also briefly, introduced you to the dispersion modeling, some basis, how it is used. And in this part of the lecture, I'll be taking you through this modeling in detail and how it is structured and how it is used, what are its uses. Okay. Welcome, Dr. Anand. So I'm about to start the lecture. I think some of few more people are joining. I'll wait for a couple of minutes before I get into the lecture. I just noticed a couple of people just joining in. Probably I'll take a moment, see that if somebody else is also trying to join before I start the lecture. Okay, so I will take this lecture in this format. I'll give a brief introduction about the modeling, how it is used, why it is, what is its importance, and then on the atmospheric transport and dispersion. Then I'll discuss on the modeling of transport and dispersion. Then with this basis, how a decision support system is organized and what are all the various elements of a decision support system and how it is used. And also give a few examples about how various modeling techniques are being used or have been used in the past, emergencies, and you can get an idea how such models helps in the overall preparedness and response of CBR and emergencies. So the atmospheric dispersion of any releases, with respect to chemical, biological, radiological, and nuclear pollutants can have a larger influence in the population because basically they can spread rapidly with extensive spatial coverage. So it has the influence of any release could be larger. So understanding the behavior of these releases in the atmosphere is of utmost important to either fully evaluate the risk or protect the public safety. Or, so this is important. Understanding the behavior of these releases is important. So for doing this, the dispersion modeling plays an important role. And of late, it is playing an increasing role in making our preparedness and as well as in making decisions during an emergency. So it can contribute to an effective risk preparedness. The modeling, dispersion modeling can help in contributing towards an effective risk preparedness first and prevention and evidence-based policy making. And it will also help during a response, during an ongoing response for any of these emergencies. So it is an important, cornerstone, I would say, of the total emergency preparedness and response framework. So I will take you to, I will just see, look at this in this way. The green one boxes are our final outcomes. Okay, that is on your right, you will have one element of preparedness, risk prevention and preparedness, and on the other side, you will have emergency response management. So for both of this area, you will have to see, for the preparedness, you will have to either quantitatively assess the consequence or risk. And for the response also, you will have to have the capability to assess the consequence on a real-time basis. So this is both is what we need. And to arrive at this, two outcomes, how we structure, how this modeling helps is, you can look at this way. And I will again show this slide in the end of, in the end of the, towards the end, where you can be able to appreciate each of these elements. So what you need basically is, what you try to do using modeling is to do these two parts, the green parts, okay, where you take certain inputs, that is release scenarios, where we mean that the type of release, what is released, the timing of release, all these inputs we take. And you also take the conditions in and around the site with respect to the meteorological parameters, we take that. And for ongoing response, you take the current response. And for preparedness, you take the historical database. So such inputs you take, and you construct first with respect to the release scenario, you construct a source term, either in the preparedness phase, based on the hazard assessment, hazard of the facility, you construct a source term. And then you make a dispersion modeling, and you evaluate the risk assessment, exposure assessment, where you get the dose perspective, what is the likely dose people are going to get, either for a planned or postulated emergency, or for an ongoing or already happened, already occurred event. So where we assess the exposure of the exposure, how much exposure public is going to get. And based on that, you assess the consequence on the risk, either on the real-time basis or as part of preparedness. So this is how you generally construct, and you can see on there is a loop here, that is a source term. So the source term is itself is an ongoing process, where you sort of, I will, just remember, I will explain you this part in the coming, in the later part of the, lecture. So this is how, in general, dispersion modeling is going to be useful for us, either in the preparedness or in the emergency response. So let us see, how do we construct this from basics, okay? So atmospheric transport, when you look at atmospheric transport, the atmospheric transport of hazardous pollutants substance consists primarily of an advection and diffusion. Okay, I think I have briefly explained you, with this graph in the earlier course, in the first part of our course. So basically, these atmospheric transport is driven by meteorological conditions that include wind field, atmospheric stability, atmospheric boundary layer heights, and and the precipitation, etc. So you look at atmospheric transport as a sink, atmosphere as a sink, but an imperfect sink, because it has a limited ability to carry away the transport, dilute, and remove pollutants. Okay, finally, it is being released to the atmosphere. So you assume the atmosphere, or you consider the atmosphere as a sink, but it is an imperfect sink in terms of its limited ability to carry, the dilute, and remove the pollutants. When we call transport, you see, it is the air motion carry pollutants from one region of the atmosphere to another. So that's part of the transport. And when we call it as dispersion, it is all about the mixing of the pollutant in the air. So this is the finer, clear distinction between a transport and a dispersion. And of course, deposition is very straightforward. Okay, so these transport and dispersion is basically dictated or influenced by the topical barriers, the local parameters, the local conditions, the hills and buildings, and the scale of air motion, atmospheric stability and inversion. This is an important part. And of course, atmospheric chemical reactions also. So let us see, this atmospheric stability and inversion part is a major aspect, okay, that governs your total transport and dispersion process. So let us see how that is, what is that about, okay? So the atmospheric stability, when I say, it's a concept that describes the movement of air near the surface. So the degree of stability, of atmosphere is determined by the temperature difference between the air parcel and the air surrounding it. Okay. And it is characterized by the vertical temperature gradient, which we call as lapse rate. And the lapse rate is defined as the rate at which the air temperature changes with height. Okay. So the actual atmospheric lapse rate, what it is, it will be somewhere approximately to -6 to -7 degrees per kilometer. Okay. But it varies widely depending upon the location and the time of the day. Okay. So adiabatic lapse rate. Okay. When we call adiabatic lapse rate, what it is? Okay. An air parcel that is warmer than the surrounding air does not transfer heat to the atmosphere. Okay, so there is no heat transfer between these parcels. Okay, any temperature change that occurs within the parcel or caused by the increase or decrease in the molecular activity within the parcel. Okay, you get it? It is the molecular activity within the parcel that is creating a temperature, gradient inside the parcel. Such changes occur adiabatically and are only due to the changes in atmospheric pressure or as the parcel moves vertically upwards. Okay. So an adiabatic process is one in which there is no transfer of heat or mass across the boundaries. Okay. As I said, there is no heat transfer between the parcel and the surrounding atmosphere. Okay. And it and in an adiabatic process, the compression results in heating, and expansion results in cooling. Okay, so this is how the temperature inside the parcel varies because of compression or either expansion. Okay, so in general, the dry adiabatic lapse rate, okay, is around point or around 1 degree per 100 meters. Okay, and the international standard lapse rate, that is the other lapse rate, that's in meters. If you should see, it is 0.006 degree per meter. Okay, so now let us see the stability condition. Okay, so now we saw what is a lapse rate, basically how the temperature changes across the height. Okay, so now we have also seen what is an adiabatic lapse rate and what is an environmental lapse rate. Okay, so you see, whenever the environmental lapse rate is much higher than the adiabatic lapse rate. Okay, you see the dotted line is the adiabatic lapse rate, and the environmental lapse rate, that is the temperature change across height, is quite high. Okay, so if this is the condition, you say the condition is unstable. Okay, and when the both of them are equal, you say it's a neutral condition. And when the environmental lapse rate is lesser than the adiabatic lapse rate, then you say it is weakly stable. And if that is higher, still lesser, they're highly, then it is strongly stable. So these conditions basically dictates your, this is used to dictate or define how the dispersion is going to be influenced. So let us see one by one how each of these lapse rates helps you in sort of changing or evaluating your how it actually influences the dispersion. Okay, So when we call it as the super adiabatic lapse rate, okay, that's unstable condition. The temperature, you see, the temperature decreases are greater than -10 degree per kilometer, and it generally occurs on a sunny day, and it is characterized by intense vertical mixing. Okay, so it is an highly unstable vertical mixing is happening, and such conditions are excellent conditions for dispersion. Okay, so these are favorable conditions for dispersion. Okay, and at the neutral lapse rate, when we say neutral lapse rate, it is the temperature decreases are similar to the adiabatic lapse rate, which we saw earlier, okay, when both are similar, okay. And this results when a cloudy conditions, elevated wind speed, and a day-night transition period, okay. These are the time when this neutral lapse rate generally prevail, and this describes a good dispersion condition, okay. So this unstable and neutral lapse rate basically, uh, are sort of favorable stability category that is good for dispersion. And isothermal lapse rate is weakly stable, that is characterized by no temperature change with height. Basically, there is not much changes, and atmosphere is somewhat stable, and dispersion conditions are moderate. And inverted lapse rate, you have, and this is characterized by increasing temperature with height. And you can see the how the inverter lapse rated is, and you can see the warmer air is there is an inversion layer, and there is a cloud, a cold air, okay. So now your dispersion does not come much below, okay. So it's sort of stable, so there is not much dispersion happening here. And you see the figure here on the other side. So it will just keep on going for a longer distance without any vertical mixing, and thereby there is no dispersion, okay. So I will take you, briefly take you through each of the stability category, okay, and how the plume is going to behave in each of these cases. The first one is the unstable category, okay, and where you have such a plume that this plume sort of a profile we call as a looping, okay, looping. And then when it is a neutral stability condition, then this sort of a plume will be there. That's a coning. And as I said, the previous one, it's a strongly stable condition. Then this fanning happens. Okay, so it can travel for a long distance without much of a dispersion. Okay, so so what happens here is basically for each of the stability category, your plume is going to behave in a different manner. And this is how you can picturize it, how it is going to behave. And the atmospheric stability condition, we have one more part is the inversion. Okay, the inversion layer acts as a barrier to vertical mixing. You see here in the lower part of the figure, the temperature, the change in temperature is different after a certain height. Okay, so at the beginning, at the lower, from the lower elevation up to the elevation at a certain height, for example, 1 kilometer, the temperature is actually increasing by height, and later it starts decreasing by height. So this distance, okay, the inversion layer acts as a barrier for vertical mixing, and it will be different for different sort of inversion. Okay, so the height of a stack in relation to the height of the inversion layer may often influence the ground level pollutant concentration during an inversion. Okay, so that is how the height of the stack. If the height is above the inversion layer, so it will help, it will not allow the pollutants to settle down. And if the height is lower, then it will be on a different case. Okay, so when conditions are unstable above inversion, the release of a plume above the inversion results in effective dispersion without noticeable effect on the ground. So this is a wonderful condition. It's called lofting, right? So the condition is unstable. Okay, above the inversion, it is unstable. Unstable means there is more dispersion. There is more dispersion means, oops, okay, just a minute. So more dispersion means that it is good, and it also doesn't allow the pollutants to settle down on the ground. Good. And there is one more condition, that is fumigation. That when the stability, when the instability, see you see the curve here. Okay, so the temperature is decreasing by height and later start increasing by the height. Okay, so this is a different sort of an inversion. At this, when this condition is, existing, this condition is there. Okay, so you will have a different type of plume, which we call a fumigation. Okay, so round level pollutant concentration, ground level. Actually, it's not round. It's ground level pollutant concentration can be very high when fumigation occurs. Sufficiently tall stack can prevent fumigation in most cases. Okay, so in this case, your stack is higher, then you can cross the inversion layer. So that is so this sort of thing dictates the choice of stack height and then the distance to it, to what extent then it is being dispersed and to what point the pollutants can actually start touching the ground. Okay. So in general, all these atmospheric stability classes, we say it as A, B, C, D, E, F. The A means it is the extremely unstable category, B moderately, C slightly unstable, and D is the neutral, and E is slightly stable and moderately stable. Okay, so the this particular characteristics of atmospheric conditions will largely dictate, and it will vary by site to site. It will vary by different sites. For example, we have various NPP sites, right? In Kudankulam, we have an NPP. We have a nuclear power plant site in Rajasthan. Okay, and there are a couple of sites like in Kudankulam, like coastal sites in Kalpakam, Tarapur, and there are other inland sites, Narora. Such inland sites are there. Basically, there is difference. Let me say that Kudankulam is having a highly unstable condition. Okay, so it will have a larger dispersion. Okay, and any releases will be different. At the same time, Rajasthan has the stability class around Kudankulam is somewhere in B and C. But in Rajasthan, you see it is dictated by a E stability class. So it is very calm wind is there, and anything that is released can travel for a longer distance. But at the same time, the site is very well that the villages in and around are very less. So there are many factors that actually come into play, and this stability class is an important aspect that governs the dispersion and the overall impact of any releases of pollutants in general in all CBRN emergencies. Okay. And windrows, you should also know about the windrows for a particular site. A windrows will give you the predominant wind directions, the wind speed that is happening predominantly. And for a valley sort of a site, you will have two-dimensional flow. It will not be distributed all around, and the flow and the speed will also be dependent upon which side of the valley the wind is flowing. Okay, but in the land and sea you have एक मिनट है, ये क्या आ रहा है, रिमाइंडर कुछ आ रहा है सनी सनी, ये कुछ रिमाइंडर आ रहा है, व्हाट इज दिस? Okay, so it's fine. It's nothing for us, right? Okay, sorry. So the land sea wind rows, the wind rows for a site, either in inland site or coastal site will be of this nature. It will have mostly of a distributed wind direction, and wind speed would be higher in a specific particular time of the day night will be changing depending, especially if it is a coastal site, your wind speed will be different, okay, depending upon the time of the day. That is, okay. Amit, welcome, Amit. Probably we have half an hour. Yeah. So I was just discussing about the basis on which the dispersion modeling are constructed. So I was just taking all of you through the stability, how the stability class is actually defined, okay, and what is its the impact on the type of dispersion it can create, and how this is going to dictate the overall dispersion, the consequence of any releases, okay. And you can see I was talking about the adiabatic expansion, okay. For example, Karamveer, welcome Karamveer. Probably Amit and Karamveer, we are quite, I mean, well past 20 minutes of the start of the class. So we might have missed a few things, but for your for your benefit, I will again uh, go through a couple of slides, okay, that will help you just to follow on, okay. That is, I was talking about the stability categories, okay, how the atmospheric transport and dispersion is actually influenced by various parameters, and one of the most important part is the stability and the inversion characteristics of an atmosphere. And I was just taking you through the various stability classes, and which class is actually good for dispersion and which is not, and why it is like that, and what sort of temperature difference is going to be there. Change in the temperature across the across the height, okay, across distance is going to be there, and how various type of plumes or how the plume will behave for different all these different type of stability categories, okay. So and I was just explaining just how we have just whatever we have learned as part of the inversion, okay. So you can visually see here uh, during the daytime, the land is uh, warmer, okay, and the warm air rises here, and the air is actually cooled by, welcome Anurag ji. So probably something might have you might have had some some other works, probably that's why you're delayed here to the class. So I was just again explaining the some basis of the uh, dispersion modeling, where I was explaining the very basic thing that actually um, influences the modeling is the atmospheric stability classes, and how the wind behaves in a day or night time. And it is all about the lapse rates, the differences between the atmospheric lapse rate and the adiabatic lapse rate. And if I was just explaining that during the daytime, the warm air rises up and it cools due to the adiabatic expansion, and it again, the cool air again sinks back to the ocean, and here high pressure is there, and the cool air flows from the sea to a low pressure area, okay. So basically it is because of the pressure difference that happens, okay, and there is no changes between the pockets, had transfer between the pockets, but it is about the adiabatic expansion of the air. And here again, at the night time, if you see, the land is cooler, the sea is warmer, Okay, and when the warm air rises up, it again cools by adiabatic expansion, and the cool air comes down, and then again the cool air flows from the land to the warmer sea in the night. Okay, so this is how the pattern sets, the wind circulation sets in. Okay. So now let's move into the modeling part. Okay, so now we discussed on how these atmospheric conditions are important, and what are the things that influences the atmospheric transport and dispersion of any pollutants, of any nuclear or radiological pollutants. Okay, so when you come to modeling these phenomena, okay, various methods can be used. And if you look at these things, various methods have been developed to simulate these transport and dispersion mechanism. And in that, broadly, you can say what are things that is used is the computation fluid dynamics. I will start from the broader aspect. Then you have this Gaussian plume. Then you have the Lagrangian puff and particle models. And you also have a chemical transport models. Okay. So broadly, you see, these are the four broad modeling methods that can be used for modeling a transport or dispersion of hazardous pollutants. So when I say CFD, it's a computational fluid dynamics model, okay, where you construct the domain accordingly and to assess. And a Gaussian plume, which we have all of us are much familiar with the Gaussian plume, which is a very simplistic model. And Lagrangian particulate, either a puff model or a particulate model, it is a little bit of an, not either a complete CFD, and it treats the particles as part of a Lagrangian as a particle or a puff. Okay. So we'll see how these various models are, what are its characteristics, okay, and how it is going to be used. First, I'll take you through the computational fluid dynamics. Okay. So CFD methods calculate the transport of pollutants based on velocity fields obtained by solving Navier-Stokes equations. Okay. So you solve the momentum energy equations, okay, Navier-Stokes equations for a particular domain. You construct it, and you use various modeling numerical techniques to do that. And near field dispersion of pollutants in the roughness sublayer of an urban environment, the studies can categorize into four typical cases. Okay, so either how do you use the CFD for this? Either you model for an isolated building. Okay, you sort of use it for an isolated building modeling, or use it for a single street canal, or use it for a array of buildings or building complexes. Okay, so by this, I think you must have now understood that such models are needed to model a complex geometry where the dispersion of pollutants are actually dictated by a local conditions, or a geometry or certain fields. Okay, so there you use a CFD, a computational fluid dynamics, and you'll see how while we are discussing the examples, you'll see how why no what of why we choose CFD for certain modeling. Okay, and the complex interactions between the atmospheric flow and buildings makes the flow structure around the building highly three-dimensional nature. Okay, so when the buildings are creating a three-dimensional flow, okay, so it is important to sort of model all that. Okay, all the impact of the local structures that will be at different heights, and what is their impact on the flow, atmospheric transport and dispersion. And you have, for that you have to employ a CFD, and it is actually computationally intensive, in the sense like the modeling time will be higher, because you have to have a finer computational domains, okay, and then all of you when you get into CFT, it's a certain basic fundamental modeling techniques and numerical techniques are used, and when you do it, it is in general a computationally intensive process, okay. And the Gaussian plume model is it's a simple approach to calculate atmospheric dispersion pollutants, which which is the first thing that anybody who wants to do a dispersion modeling to start with, you can start using a Gaussian plume model. But at the same time, you cannot use a Gaussian plume model for a study inside a building or inside an array of buildings. Anyway, it will not work that way also, okay. In general, if it is being released at a atmosphere which is free of local impacts, you can generally use a Gaussian plume model, okay, and it has its own limitations in the way that a number of simplifying assumptions have to be made for the original three-dimensional advection diffusion equation to obtain an approximate analytical solution. Because if you want to make it simpler, when you're solving this three-dimensional diffusion equations, you have to make many simpler assumptions. And some of the assumptions I put it here. It is that the release rates of pollutant is constant from a single source. The wind velocity is constant along x-axis, that is the flow, and the change in velocity, treatment of changing velocity will be difficult, and the dispersion is in a steady state independent of time. So the dispersion is not changing by time, and you also don't consider the eddy diffusivity are only dependent on the downwind distance. You see only at the downwind distance there is an eddy diffusivity, okay, and the topography is flat. The transport in the x direction is dominated by advection, and diffusion is negligible in this direction. So the diffusion you only take in the vertical directions, okay. So in the x direction, the diffusion is negligible. These are the assumptions that we make when we do a Gaussian plume model, okay. And when you come to the Lagrangian model, the Lagrangian model calculates the transport of pollutants by utilizing a series of released puffs or particles, okay. So which we call, which can carry a certain amount of released pollutants and are transported downwind, okay. So the treatment is based on a puff or a particle, okay. The concentration are calculated using the total amount of pollutants carried by all the particles within a certain volume. And Lagrangian models are much more flexible and powerful than the Gaussian plume model, because we have just discussed the assumptions that we have made, the limitations that are part of the Gaussian plume models. So in general, the Lagrangian models are much more flexible and are powerful, okay, and they can treat discrete puffs or particles, and they can be used across complex wind fields and complex terrains also to simulate the transport of pollutants in different type of topographies. So which is a limitation with respect to the Gaussian plume model, okay. So there we assume the topographs is actually flat, okay, and they can also be applied to unsteady situations with changing release conditions, changing emissions or pollutant release, as well as temporal or spatial variation in meteorological conditions. Basically, you can treat these changes, changing weather conditions, which we were not, like in the Gaussian plume, we have taken an assumption that the velocity is constant in the x direction, okay. So here you can treat this changing velocity and temporal profiles of wind as well as the release parameters, and they are widely used owing to their relatively low computational cost. This is not that computationally intensive as like your CFD models, okay. And it should be noted that the computational cost increases with increasing number of puffs or particles. So when you want a much finer domain, finer results, when you want to increase the sensitivity of these modeling, then probably you will have to invest more on the computational aspect. Okay, and if the distance between the neighboring puffs or particle become too large, then the estimated concentration field will become unrealistic and discontinuous. Okay, so you have to accordingly select a domain size that is appropriate, and these are part of optimization of the models that you create. Okay, so that's a part and parcel of any modeling you do, and where you do a sensitivity study, which node side works, which node side doesn't work. Okay, but sensitivity study, we mean like you do a nodal sensitivity study where when you say how do you choose a node, node sizes, is that you keep you have to do analysis and see that there is no further change in the quality of results. Okay, for further change or further refinement of the nodes, or for such a lower node conditions, there is a large variations in the output. So that is how you understand what is the impact of the node sizes on the modeling, on the outcome of the results. So here you should also take care of this. And the problem may arise when applying Lagrangian models to large scale studies. Okay, so it is like a between CFT and Gaussian plume model. If you want to use it for a very large scale, probably you will have certain problems, and probably you will have to have more computational cost will be increasing. So in general, this Lagrangian model is probably a good fit in many of the cases, which has certain advantages from the than the Gaussian flow model, and also it has certain disadvantages in sort of when you're trying to model a large scale studies. Okay, and it is also not that computationally intensive as in the case of CA. Okay, and you also have chemistry transport models. Okay, the chemistry transport models calculate the spatial and temporal evaluation of the atmospheric concentration of pollutants, which is governed by the advection, diffusion, reaction, partial differential equations. Okay, so you basically solve this partial differential equations, and the key physical and chemical processes are modeled by chemistry transport models, including advection due to wind transport, diffusion due to turbulence, and reactions due to physical and chemical processes. Okay, so in general, global or regional chemistry transport models, such as there are some of these are some of the tools that are used for chemical transports. That is GEOS, Chem, Polaris 3D, CMAQ, and WRF Chem are widely utilized to investigate and regulate air pollutions. Okay, so these are some of the tools that is used. I will also take you through in general what are the tools that are used. Okay. So far, we have seen the different types of models that are available, right from computational fluid dynamics, Gaussian plume, Lagrangian particulate, and chemical transport models, and we have seen the how each of these models are what are the characteristics of each of these models, and what are the benefits and positives of benefits and the limitations of each of these models. And because you will have to choose the modeling techniques according to the application. Okay, so that you will see later part. Okay, so you will have a flavor when you choose a computational model, or when do you choose a Lagrangian model. Okay, so that we can see when we look at some of the applications. Okay. So it's this is the first. I mean, we have seen the dispersion part. We need to also look at the assessment of exposures, where I'm just giving one of the example for the nuclear exposure pathway assessment, exposure assessment for using different pathways for nuclear emergencies. So where you have an atmospheric route, which I think I've briefly discussed in the previous, the first part of our course. That is the atmospheric route. You have a plume dose, inhalation dose, ground shine dose, ingestion doses, and some of the things that you consider in calculating all this. Most of you are aware. And the aquatic route, the consumption of contaminated water for drinking and cooking. So this is going to be important thing. And we have 5 minutes. 5 to 6. 5 to 6 minutes. Okay. So so basically, these are the pathways that you consider for as you know, estimating the exposure pathways. Okay. So this is one aspect of it, and I will quickly take you through some of the tools that are being used for for various modeling applications. So you see this flux part, okay? It's a particulate, it's a Lagrangian particulate model, okay? So I have also put the references if any of you are interested in reading further of these models. Each of these models have their own, modeling strategies and modeling approaches, how it is constructed. And so you can look at these reference papers, and then you can have your own self-reading, and then you can understand better how these models are actually each of these tools basically are modeling tools are used and how it is done. Okay, so flux part is an important model. This is a Lagrangian particulate model. This is probably, I would say, uh, workhorse. Okay, going to be workhorse, or people are you have to move away, move further from the Gaussian plume models. So the flux part model is a good candidate in many of the cases. Okay. And regional atmospheric transport models, there is PD, system for prediction of environmental emergency dose information. This is one of the tools that is used in Fukushima during Fukushima responses, and worldwide SPIDI and improvement of the SPIDI models. And RIMPUF is also an important model that is used in many of the dispersion or decision support system tools. So why I'm taking you to these specific some of the tools is that any use of these dispersion models or your understanding on a decision support system will be based on these informations. Okay, and you also have this split method, that is hybrid single particle Lagrangian integrated trajectory model. This is also one of the good models. Then you have this Rhodos, basically that it uses Lagrangian puff model basically, and the atmospheric dispersion model system ADMS, and hotspot. Hotspot is basically based on a Gaussian plume model. Okay. So these simulation tools can be used to model the radioactive sources discharges to the environment and to provide atmospheric dispersion predictions and comprehensive analysis to support emergency planning and environmental impact assessment. Okay, so these are so depending upon the type of application you are using, and the domain and the release patterns, the surrounding conditions, the topology, everything. So you accordingly choose these models for your application. And some of these tools have integrated atmospheric models, dose assessment models, and pre-processing functions. Okay. So as you say, a few tools restrict themselves to only dispersion, atmospheric transport, and a few tools have their own integrated atmospheric transport and as well as exposure assessment. That is the dose assessment modules. Okay. So in the exposure assessment, you generally calculate the dispersion and the concentration, which I discussed in the first part of our course, that where you calculate the time integrated concentration at any locations. Okay, so so that is the part. Probably I can take you. Just can you put this pen drive? Okay. I was telling you about this time integrated models. Okay, so I will explain you a little bit. Yeah. Each one. HBNI, that folder. Just a minute. Sorry. I'll do it. No, not this one. Not this one. उसके पहले वाला, just not about. नीचे आ जाएगी, नीचे बस ऊपर पे, ऊपर नहीं, और ऊपर, और ऊपर, और ऊपर, ऊपर, हाँ, और ऊपर, बहुत, हाँ बस. So, इसको just इसमें डाल दीजिए. So for any calculations, you generally estimate the time integrated air concentration. I'm just going to just tell you just to link to the previous slides which I was talking about. So you can use a simple Gaussian plume model and calculate the air concentrations. Okay. So where you identify the chi by q values, that is the concentration at any location. Okay. And the release rates and the wind speeds. By using all these parameters, you can identify, you can calculate the air concentration. And then, as I was telling, for a Gaussian plume model, you can calculate the sigma y and sigma z values, and then for a given plume. Okay, so then you can identify the time integrated concentrations, basically, which is basically dictated by your release wind speed. Okay, and this sigma y and sigma z, which you have actually derived from the previous one. Then you also take care of downwind distance in the directions and the distance in horizontal plane. Okay, so an equation is constructed this way, and you can use this time integrated concentration. Sorry, you can estimate the time integrated concentration. Okay, so that way you can actually use these models to estimate basically the dispersion, the level of concentration in the air, and what is being deposited, and also construct the exposure situation also. That is, what is the dose. Okay, the conversion of dose is very easy, that you calculate a concentration and then you have a dose conversion factor. This is specifically for nuclear. And for other CBRN emergencies, you will have the dose, exposure modeling also in their own calculations. Okay. So these are some of the things that tools that are used. And in the next class, I will, I will again discuss, okay, some of the applications of these tools, where it is applied, and how I will give you flavor on that. And also then I will take you through the decision support tools, how these decision support tools are actually constructed based on these models. Okay, so where certain important aspects for decision support, see, a tool, when you construct a tool for decision support system, it should have certain elements, okay, which actually is helpful, okay, for making decisions. Okay, so otherwise you also have, for understanding of these things, you can use this model and to see the scientific basis about how this is happening and how transport and dispersion is happening, you can see. But when you call a dispersion tool, it needs to have certain elements. Okay, that is actually helping us in making decisions, which we will discuss in the next class. Okay, that is tomorrow's class. Okay, so until then, if you have any questions, you can please let me know. I'll be happy to clear your doubts. And if not today, probably tomorrow also we can discuss on that. The questions are? Which questions are? बंद हो गया ना अभी तक नहीं हुआ. I think if we don't have any questions, probably we can close today's lecture. Okay. So probably you can leave us some, any of your questions, or I can address it to tomorrow's class as well. Do we have any questions now? So we can close. Okay. Thank you.